In this next video, we're going to have 6 examples of using the perpendicular and the angle bisector theorems and their converses. In this first problem, we have the segment ML, and when it has a line going through it, this line NP, that is both perpendicular and bisecting the segment ML. Since N is on the perpendicular bisector of the segment ML, we know that N is equidistant to the two endpoints M and L. Therefore, the segment length LN is equal to the segment length MN. It's also given that the length of LN is 2.6, and therefore, by substitution, the length of the segment MN is also 2.6. In this next diagram, we have a segment BC that has a red line that is perpendicular to it. It does not show that it is bisecting the segment BC, but there is a point on the line DA, this point A, that is equidistant to points B and C. In this problem, we're asked to solve for the length from B to C. And we can see that this segment BC is made up of two smaller segments, the segment DC and the segment BD. Since A is equidistant to both B and C, meaning the segment length AB is equal to the segment length AC, and that the line DA is perpendicular to BC, both of these two conditions are important. We have to have equal distance to the endpoints and on a perpendicular. We then therefore know that the line DA is in fact a perpendicular bisector of the segment BC by using the converse of the perpendicular bisector theorem. And therefore the segments DC and DB are equal in measure. With the segment addition postulate saying that the segment BC is made up of the two pieces DC and DB, we can substitute in that both of those segments would be 12 units long, and therefore the length of BC is 24. In this third diagram, we have a segment TV that has a perpendicular bisector, the line UW. We can see that the point U is equidistant to the points T and V. What we're here to solve for is to find the length of the measure from T to U. Because of that the line UW is a perpendicular bisector, we know that therefore that the segment length TU and the segment length VU are equal in measure. We can substitute in their expressions, subtracting 7x from both sides and subtracting 9 from both sides, and then subsequently dividing by -4, we get that x equals 6.5. In this problem, we weren't asked to solve for x, but we needed to solve for x so that we could substitute it back in to the expression for the length of TU and simplify to get that the length of TU is 28.5. We're going to shift gears now and use the angle bisector theorem. And so here we have an angle with an angle bisector coming through it. And now it has some labels and some information in it. We have the angle BAD with its angle bisector, the ray AC. And we can see that C has a distance to the side of the angle, this distance C to D, we know that's the distance because it's the perpendicular distance, is 7.2. Now, since C is on the angle bisector of the angle BAD, with BC, the segment BC, and the segment DC perpendicular to the sides of the angles. Remember, this is very important. It's this perpendicular distance. It's not just any distance. We can say that the segment BC and the segment DC have the same measure because of the angle bisector theorem. And it's given that the length of one of them is 7.2, so the length of the other is also 7.2. In this diagram, we have an angle EFG, and it has a line going through it, this line FH. It's not shown that it is an angle bisector. It is just shown that it has a point on it, this point H, that is equidistant to the sides of the triangle, excuse me, the sides of the angle. And what we want to do is we want to find the measure of EFH. Now the measure of EFH, that is this smaller angle right here. And that's what we're out to find, is the measure of that little angle, given that the larger angle, EFG, is 50 degrees. Since it's given that this the distance H to E and H to G are the same, that those distances are the same, and that it's perpendicular to the angle, we know that the ray FH is in fact an angle bisector by the converse of the angle bisector theorem. And therefore, the measure of angle EFH is half of the measure of the angle EFG. So that small angle is half of the large angle. We can substitute in the 50 degrees and then simplify, and then we have the measure of the angle EFH is 25 degrees. In this last problem, we have, it's a very similar in how the previous problem looked. We happen to have an angle JKL, and we have a ray KM, and this point M is equidistant to the two sides of the angle. And since this M is equidistant, and it's perpendicular distance, it's equidistant, we therefore know that the ray KM is in fact an angle bisector. And if it's an angle bisector, then those two angles are the same in measure. And so we can set them up as equal to each other and subtract to solve and get that the measure of that the value of A is 6. We still have to substitute that back in so that we can find the measure of angle MKL, and so we substitute it in, and then we simplify, and we get that the measure of angle MKL is 38 degrees.